All right, so in chapter 17, we discussed how stable benzene rings are. This means they do not react as readily or as fast as an isolated double bond. Look at a bromination reaction. We see that Br2 can react very readily with an isolated double bond, but if it's used on an aromatic compound, nothing will happen. However, when we add some iron along with the Br2, we will get a substitution reaction of a benzene ring. As you can see, treating a benzene ring with both Br2 and iron results in a different type of reaction, a substitution reaction, where we have a bromine atom substituting for a hydrogen atom on the aromatic ring. We can do several different types of substitution reactions to a benzene ring. These reactions are referred to as electrophilic aromatic substitution reactions. And this is because we will react the benzene ring, which is going to react to something called a nucleophile, with an electrophile to get a substitution reaction. All right, this is where the electrophile that we're reacting the benzene ring with substitutes for a hydrogen on that benzene ring. All right, so now let's take a step back and talk about exactly what are nucleophiles and electrophiles. All right, from the name nucleophile, we can ascertain that it is a molecule or an atom that loves a positive charge. Okay, phile meaning love, nucleo referring to the positive charge on the nucleus of an atom. Okay, nucleophiles, as you will see in this chapter, in the rest of Orgo 2, are atoms with lone pairs, atoms with negative charges, or pi bonds. So some examples are listed here. Okay, we have water, which has an oxygen atom, which we know has 2 lone pairs. Those lone pairs can act as nucleophiles, allow oxygen to act as a nucleophile. Any atom, here we have a sulfur, with a negative charge, will also have at least 1 lone pair and can be attracted to something positively charged, act as a nucleophile. Okay, we are going to specifically be looking in this chapter at pi bonds acting as nucleophiles. That extra electron density in those p orbitals can be attracted to positive charges and allow a reaction to occur. Electrophiles are essentially the inverse of this. They love electrons. These are atoms with either a positive charge or a partial positive charge caused by a polar bond, right? An example that you've seen before, a proton, okay? It's got a positive charge. It's gonna be very attracted to negative charges, okay? A carbon that's part of a carbonyl. It's got that really polar carbon-oxygen double bond. That leaves a partial positive charge on that carbon, making it prime for a nucleophile to attack. We will start with what is known as a halogenation reaction, the one we saw at the beginning of these slides, right? When we treat a benzene ring with bromine alone, nothing will happen. However, when we treat benzene with bromine in the presence of iron, we will see that we actually do get a substitution reaction. Okay, why is this? Well, the iron reacts with the bromine to create iron tribromide, as we see here. Okay, this is a Lewis acid catalyst, so it can accept a pair of electrons from another Br2 molecule. This makes bromine a great electrophile. One of the double bonds on the aromatic ring can then act as a nucleophile and attack the bromine that's attached to the iron tribromide. This will then create a resonance stabilized carbocation. right? The resonance stabilized carbocation is referred to as a sigma complex, right? And we can see the different resonance structures here of how that positive charge is moved around and stabilized. The sigma complex is then re-aromatized when the bromine iron tribromide complex abstracts a proton from the same carbon that the bromine added to, right? The electrons from the carbon-hydrogen bond go back into the ring to re-establish aromaticity in reforming that third bond. Now, just as easily, we can use chlorine instead of bromine, right? These are actually the only two practical halogenations. We have 4 halogens, but these are the only 2 reactions we can do. Fluorination using fluorine, it is very violent. We don't want to do that. And iodination is really slow with very low yields. The mechanism for chlorinating a benzene ring is analogous to what we saw with bromine. Chlorine and a metal, either aluminum or iron, it could be either one, are added together along with a benzene ring. A Lewis acid is formed, and in this example, it's AlCl3, that can now accept a pair of electrons from chlorine, Cl2, which turns that chlorine into a very strong electrophile. This will then allow one of the double bonds of the aromatic ring to attack the chlorine to form that sigma complex intermediate. Okay, a chloride from the newly formed AlCl4 then abstracts a proton from the same carbon that the chlorine added to. Those electrons from that bond go back into the ring, reestablishing aromaticity.